Everyone, this is Mrs. Lindsay Pereira again, and today we are going to start section 1-2. The notes for this will be out of our student journal, so if you can turn to page 9 in your student journal, that would be great. If you don't have it, please pause the video, go get it, and then we can resume. So today we're really going to be talking about constructing segments, and we're going to talk about what it means to be congruent, and we have what we also call the addition postulate. Okay, let's jump in with our first postulate here. Points on a line can be matched 1-to-1 with real numbers. Okay, the real number that corresponds to a point is the coordinate of the point. Okay, the distance between these, and this example over here to the right, A and B, written as AB, is the absolute value of the difference of the coordinates. So you really can mark these. You can kind of think about it in terms of a number line. You know, if I have point A and B, this could correspond to, let's say, 1 and 5. Well, what they're saying is then the distance between A and B would be 5 minus 1, which really would just be 4. Okay, now the reason they talk about absolute value is because these could be negative. Okay, so if I have a negative distance, or again, you can think about counting in between there. If I go from 1 to 5, I got to count up 4 places to get to 5. But if I have something that's negative, let me just make another example here. I'll call this X and Y. So we'll make this one, let's see here. Let's just change it and make it -1. I'm changing my mind as I'm writing that. Let's do -4 and -1 over here. Okay. So the absolute values of this, so what I did here was 5 minus 1. So again, you can think about it as counting. If you're doing that, again, you might think, okay, XY has a distance of 3, because I got to go from -4 to -3 to -2 to -1 on your number line. But again, you can also use the absolute values of those. So if you do that, notice the order they have here. They have the one on the right, which is always the larger number. Okay, so they have this as XY is the larger number is -1 minus a -4. So this really turns into -1 plus 4. You'll see me do this notation quite frequently. If you want to write that extra step out, completely fine. My 4 looks a little odd there, so let me rewrite that. So now I add those together, I get 3, and the absolute value of a positive number stays positive. If that was absolute value of -3, it would go to positive, but the distance there is 3. Okay, so that is what is meant by the ruler postulate. Okay, I won't really use that terminology a whole lot. Occasionally the book does, but really I just want you to realize that we're kind of really referring to a coordinate of a point here. Congruent segments. Again, this is a really crucial topic that we'll talk about all the time. And we talk about congruency with all types of things. Segments, triangles, all sorts of different things. Different types of polygons, etc. Okay? The symbol that means congruent is right here. It is comprised of the equal sign, right here, and the similar sign. They don't really show that right here, so I'm going to kind of put that in here. So we have the similar symbol. That is just a little squiggle. So if you put this equal sign with the little squiggle, that is your congruent symbol. An equal sign with a similar symbol on top. Again, we will use that frequently there. Okay. This means segments are congruent. Okay, equal means, again, lengths are the same. Similar means they're the same object. So in this case, we're talking about segments. Okay, so if you see something like this, which says AB is congruent to CD, these two segments, so they're referring to these. Notice there's a little symbols on here. There's a little mark on each of those. So whether it's written out as a congruent statement or it's symbolically shown on a diagram. If you see that line and that line, you know that this is the same length as this one. It's the same shape, which is a segment, and it's the same length. Okay? So again, they're referring to that up here in terms of lengths, that they're going to be congruent to each other. All right, and again, there's a bunch of different types of congruencies. Let me show you something on. I'm going to put a few points here on it. Okay, if you see 2 tick marks, okay, this means segment AB is congruent to segment BC. So again, they have the same length. So I don't have to have 2 separate diagrams. It could be on the same one. Okay, and again, notice I'm pulling off segments off of here, off of this diagram. I don't know why this keeps highlighting that. Okay, I'm pulling the segment off of here and a segment off of this entire line. Okay, I could also have, let me just point out another example here. A whole bunch of those, so go ahead and take a moment, write those down, and we're going to write some congruent statements with this one. I'm going to give myself a little bit more room here. Okay, so hopefully you have that written down as I'm moving these down. Okay, so let's talk about what's congruent here. I see one line here that is congruent to the matching symbols. You have to be able to match symbols. So in this case, AB, segment AB is congruent to segment XZ. Okay, so let's see if we have any other symbols. Now I have the double lines. Yes, there's a double line over here. So I would say BC, segment BC is congruent to segment YZ. So I know if this is length 5, this is also length 5. Okay, so let's see if we have anything else. Now I have like a little arrow. I have no arrow over here. It does not match. The only thing I have over here is a circle. They don't match. They are not congruent to each other. Okay, so again, the symbols must match. And just because AB is congruent to XZ, that doesn't mean they're all congruent to each other. Just AB is the same length as XZ. Okay. So again, we can visually look at them in the diagrams that look like this. We can also talk about them in a coordinate plane. Okay. So we're going to take a look at these. It says we want to determine whether segment AB and segment CD are congruent. So I'm first going to graph AB. So I have -5, 5, and -5, 2. Okay, so I'm going to make an XY coordinate plane. So I'm going to just kind of go right in the middle here with both my X's and my Y's. So this is my X, this is my Y. So if I graph, I'll do this one in red, -5, 1, 2, 3, 4, 5, up +5, 1, 2, 3, 4, 5, and I'm going to label that point as A. And now I'm going to graph B as well, -2, and then up 5. So here is segment AB. Now in this case, we can visually, since it's on a horizontal line, we can visually and count. It's like it's on a number line, okay? So in this case, so 1, 2, 3. That has a distance of 3, so that is my length. Now I'm going to do CD. So I have 2, go over 2, down 4. That is C. And I'm going to do the same with D. -1, down 4. So here's my segment. Again, I can count. Always, again, go right to left, just like you're graphing here. 1, 2, 3. Yep, they are the same. So yes, they are congruent. So let me go down below. Yes, AB is congruent to DC. And again, put those symbols above. If you don't have those symbols on there, that is not correct. Okay? We're going to skip number 2 for right now. Okay? I would like you to do number 3 on your own. Okay? Skipping this for a moment. Don't completely cross it off. We might come back to it a little bit later. But do number 3 and then answer yes or no. Is AB congruent to CD? Okay? And then when you're done, push play to check your answers. Okay, so here's the answer to number 3. They both have a length of 6, so yes, they are congruent. I do want to point out one thing. Notice over here in the green, number 3, I wrote CD. Over here, I wrote DC. Doesn't matter. That's still referring to the same segment, no matter which order I put those in, because the endpoints are the same, right, on a segment. So just FYI with that. Doesn't matter which direction I really write CD or if I wrote DC. That is the exact same segment. Okay. All right, so let's talk about the addition postulate. Okay, so over here to the right, we have our diagram. So the whole thing here is AC, and notice how they're using these markings. You'll see me do this type of thing on a diagram. So in geometry, it's very important to do a couple things. Write the diagram down, and then label the diagram. Very, very important. You're going to see me do all these steps all the time. A lot of times, a lot of your work is going to be done really right on the diagram. Okay, so don't be afraid to actually write that diagram down. Again, I will constantly be reminding you of that. Okay, but the addition postulate is just this. So if I know the distance of AB, and I'm going to say that's 3, and I know the distance of BC, and again, I'm just going to say that's 2. Well, I know AB plus BC equal this total segment of AC. So AC would then be 3 plus 2, so AC would be 5. Okay? And we're going to do a lot of examples with this. So let's try some of these. Okay? So in this case here, it's a little given to us a little bit differently in number 4. They give us the whole amount VU, then they give us WU. So now we're trying to find this remaining portion. So it's kind of the reverse of the addition property. VW would be the larger segment VU minus the smaller WU. So 31 minus the 8. And that's going to give us 23. Okay. Same idea here with number 5. They give us the larger amount and the smaller portion. We only know a portion of it is 6. So VW would be the larger portion, 18, minus the smaller portion, 6. So that would give us 12. Now 6 is stated the way the actual postulate is. I know part of it, UW is 45 and UV is 30. So if I'm looking for VW in this case, I've got to add both of those together. So 45 plus 30, that would give me 75. And again, those are segments that we're referring to. Okay. So that is the addition postulate. Again, I don't always refer to that by name. Occasionally the book will. I just basically will use it just like these examples here. Find the various length of a segment. All right, so let's try the word problem here. A bookstore and a movie theater are 6 kilometers apart along the same street. A florist is located between the bookstore and the theater on the same street. The florist is 2.5 kilometers from the theater. How far is the florist from the bookstore? Now I know that's a little wordy, but the first thing that you want to do is read it, and then we're going to go back and we're going to draw a diagram, and we're going to take it sentence by sentence and form a diagram. So let's look at the first sentence. A bookstore and a movie theater are 6 kilometers apart along the same street. So I'm going to say, here's my bookstore. Here's the street. 6 kilometers away is my movie theater. So I'm going to put M for movies. So I just did the first sentence. Now I'm going to read the second one. A florist is located between the bookstore and the theater on the same street. Ah, okay. So let me add that in. Actually, I'm going to move this 6 here just a little bit because I have to put something in the middle here. So I'm going to just label this as 6 right here. So I know between the bookstore and the movie it's 6. So now I'm going to say, okay, again, a florist is located between the bookstore and the theater on the same street. So it's got to be on this street. Somewhere in here is my florist. Okay, so I just did that. The florist is 2.5 kilometers from the movie theater. So I actually drew it a little off scale. 2.5 from the florist to the movie theater. Okay, 2.5 goes here. I drew it so it looks like this is a larger segment, but I didn't realize that. That's okay. Sometimes you can't make assumptions from your diagram. So never assume that your diagram is, for example, like a 90-degree angle, or that one segment is smaller than another one. You can't make those assumptions. I know that seems a little odd, but you can't make assumptions from diagrams. Okay? So now it says, how far is the florist from the bookstore? So florist to the bookstore, that's what we're looking for. We're looking for BF. And I can also just call it X. So again, I know the larger portion is 6. I need to subtract off this smaller portion of 2.5. And I get from the bookstore to the florist, it's going to be 3.5. And I'm going to label it kilometers. When you get to a word problem, I'm not asking you for a sentence or a paragraph as an answer. I expect you to label it. Okay? So, recapping. We read the problem. Then, we took it one sentence at a time. And we drew a diagram. Okay, then we can actually solve the problem. And then we labeled our answer. Okay, so that's kind of the strategy that we're going to talk about whenever we're working with word problems and such. Read it through all the way once, take it one sentence at a time, form a diagram. From the diagram, so notice again how I should put in here, I really labeled my diagram too. Okay, so you want to label your diagram. I have all sorts of numbers and variables on here. Label it, pull off your algebraic problem to solve it. So this is going to be your algebra equation. And then label your answer. Okay? All right, last but not least, I want you to finish this up on your own. Flip back into your journal here. In your own words, I would like you to write the meaning of each of these vocabulary terms from what we just talked about. And we'll kind of recap those from when we come back to class, okay? This one, the hint for this one, you might want to look at what we did with this. Notice the word between is right here in number 7. So think about that one just a little bit, okay? But congruent segments we talked about, and then between us we talked about in problem 7. So wrap those up, and then we'll discuss them in class.